Most of the really fundamental questions of where, when, and how fast in simple harmonic motion can be answered by conservation of energy. For instance, it's obvious that the fastest a spring will be going will be located as it passes the equilibrium position when it's got no spring potential energy whatsoever and all of its energy is kinetic energy. Just like it was obvious that the maximum acceleration will be found at the very, very edge when x is at its maximum displacement by Hooke's law. It's worth plugging in everything we got from our differential equation and from our first derivative into the old conservation of energy formulas that we had back from first year physics, 1/2 kx squared and 1/2 mv squared. Once you plug them in, you notice something amazingly cool. Yeah, you got all this weird a squared cosine squared stuff. But when you get to the velocity, the m's cancel out, and the cosine and sine are cosine and sine of the same quantity, and that means you can use a Pythagorean trig identity and get rid of all this garbage, getting, as we derived, the formula you started with last year for the total energy of a simple harmonic oscillator. Now that you know that 1/2 mv squared plus 1/2 kx squared always is going to equal the same total unless there's mechanical work being done, in which case conservation of mechanical energy is not holding. Rearrange this to solve for V. This is a tremendously important shortcut because this means calculus. This means more calculus. But if they ask you where, at what physical location is something going to be going that speed, you don't need calculus at all. You're one step to the answer. Pause. Check your work, box the final equation in your physics notebook, cover it with little stars and things because it's one of the greatest shortcuts in this chapter, and remember this for future use.